Tick-tock. No, not the app, a clock. You see, scientists already know the exact doomsday date. Tick-tock. The countdown has started. We only have 250, no, not years, millions of years left on this beautiful planet we call Earth. Well, let me apologize first. I might have scared you with all these end-of-the-world things. You and I certainly won't live to witness it, but we already know when it will all go downhill, and most importantly, why. This 250 million years deadline is not precise. If we change our ways, humans can stick around for more or less, depending on what way we choose. Researchers ran some computer simulations and found that Earth might be left without any mammals if temperatures kept climbing to between 104 and 158 degrees Fahrenheit. What's the culprit? Well, it's mainly our love for fossil fuels and the greenhouse gases we keep pumping into the atmosphere. It's easy to think that mass extinctions are a thing of the past, especially since the last big one wiped out dinosaurs 66 million years ago. But surprise! We're actually overdue for another one, and this time, it's all on us. Throughout Earth's history, there have been 5 mass extinctions, and it's been 66 million years since the last one. But this upcoming one is special. It's totally human-made. As Earth's tectonic plates shift over millions of years, they eventually come together to form supercontinents. This could lead to some pretty serious natural disasters, and, well, it might as well mean the end. Having one continent instead of 7 is already pretty extreme, as it will totally make us rethink the way we live. Now, scientists said that a new supercontinent would create a trio of problems. The continentality effect. No, I didn't make that word up. A hotter sun, and rising CO2 levels, resulting in a super hot planet. This would lead to tough living conditions for mammals with limited food and water. If temperatures hit 104 to 122 degrees Fahrenheit, and maybe even more extreme fluctuations, humans and lots of other species would struggle to cope since we can't shed heat effectively through sweating. Some experts believe the future looks pretty grim. CO2 levels could end up being double what they are now, and the sun's radiation could increase by about 2.5%. With the supercontinent likely to be in hot, humid tropics, much of the planet could be facing extreme heat. Finally, in about 250 million years, Earth is expected to morph into a donut shape with a big inland sea in the middle, leaving the Pacific Ocean to cover most of the surface. Honestly, no matter how well scientists crunch the numbers, they can't see the future, especially when it's this far out. But hey, those who ignore history are doomed to repeat it. So let's jump into the history of the 5 massive extinctions that have already happened. The late Ordovician mass extinction hit around 445 million years ago and was a huge deal for ocean life, wiping out up to 60% of marine species, including 85% of all marine creatures. Unlike other extinctions, it really didn't change ecosystems much. It had 2 main phases. First, the climate cooled due to glaciation, causing sea levels to drop and many marine animals to lose their homes, leading to new cold water ecosystems. Then, when the ice melted, warming returned, but oxygen levels plummeted, creating toxic ocean spots. I know, it all sounds horrible, but let's see the results. The planet is still habitable, marine life is booming, and, by the way, there are even species, some hard-bodied arthropods like horseshoe crabs, that are still around. So from our perspective, it feels like it wasn't a disaster so much as a step for further development of our planet. But let's not make premature conclusions and take a look at the next mass extinction. The late Devonian extinction was a big deal in Earth's history, happening about 272 million years ago. The main event during this time was called the Kielwasser event, which wiped out about 19% of all family groups and half of all types of living things in the oceans. Another extinction, the Hagenberg event, occurred around 359 million years ago and marked the end of the Devonian period. This extinction wasn't just one event, but might have happened over a long time, possibly from 500,000 to 25 million years. Some scientists think that there were as many as 7 separate extinction events during this period. By the late Devonian, plants and insects were starting to thrive on land, and oceans were filled with huge coral reefs. The continents were also moving together to form what we know as Pangaea. Most of the creatures that disappeared were in the oceans, like brachiopods and trilobites, especially the ones that built reefs. The reasons for this extinction are still a mystery. Some ideas include changes in sea levels, lack of oxygen in the ocean, global cooling, or even volcanic activity. There's also a theory that a comet hit Earth. Interestingly, it seems that the loss of diversity came more from fewer new species forming rather than a spike of species dying out. During this extinction, oceans became low in oxygen, which helped preserve some organic material. This, along with the porous rocks from that time, made Devonian rocks a valuable source of oil, especially in places like Canada and the US, way before they became Canada and the US. So far, these terrible mass extinction events don't sound that bad. Now, about 250 million years ago, there was a huge event called the Permian-Triassic extinction, often called the Great Dying. It was probably the worst extinction event ever on Earth. During this time, a whopping 59% of all biological families and 83% of different kinds of living things disappeared. This included 81% of marine life and 70% of land animals. Even insects were hit hard. Scientists believe the main cause of this mass extinction was massive volcanic eruptions in what we now call the Siberian Traps. These eruptions released a ton of gases, like sulfur dioxide and carbon dioxide, which messed up the oceans and made it hard for many creatures to survive. The atmosphere's carbon dioxide levels skyrocketed from about 400 parts per million to 2,500 parts per million. Other possible reasons for this extinction include burning oil and coal during these eruptions, intense weather patterns like El Niño, and even a possible asteroid strike. All of these factors combined, creating a really tough environment for life on Earth at that time. Okay, this one seems serious. Let's proceed though, shall we? The Triassic-Jurassic extinction event, happening around 200 million years ago, was a major wipeout of many species, both on land and in the ocean. In the oceans, between 23 to 34% of marine life vanished. On land, most reptiles, except for crocodiles, dinosaurs, and pterosaurs, those flying reptiles, went extinct. Some of the reptiles that went extinct were once very common. Luckily, plants, early mammals, and the groups that survived, like dinosaurs and pterosaurs, thrived and became the main animals for the next 135 million years. Scientists think this extinction might have been caused by huge volcanic eruptions, which released lots of carbon dioxide into the air. This led to global warming and made the oceans more acidic. The Cretaceous-Paleogene extinction event happened around 6. Oh boy. Scientists predict a volcanic eruption that is likely to be one of the most destructive in the history of our species. There's a 1 in 6 chance of it happening in this century, and it could seriously change the climate even more and put millions of lives in danger. Back in January 2022, the Hunga Tonga Hunga Ha'apai volcano erupted in the South Pacific Ocean, creating a huge explosion. It sent tsunamis all the way to Japan, North America, and South America. Tonga itself was hit hard, with damage costing nearly 20% of the country's entire economy. Now, researchers at the Niels Bohr Institute in Copenhagen have studied ice samples from Greenland and Antarctica, and their findings are worrying. predicting potential global volcanic disaster. They say there's a real chance of a much bigger eruption, a whopping 10 to 100 times larger than Tonga's. In the past, eruptions this size used to change the climate and even cause civilizations to collapse. Despite future volcanic eruption risks, experts say the world isn't prepared at all. Michael Cassidy, a volcanologist from the University of Birmingham, warns that no sufficient effort is made to handle a disaster like this. He says that NASA and other space agencies spend billions on asteroid defense. At the same time, a volcanic supereruption is way more likely than an asteroid impact. And right now, there's no global plan for dealing with a massive eruption, even though it's likely to be far more destructive. The last magnitude 7 eruption happened in 1815 at Mount Tambora in Indonesia. Then, thousands of people lost their lives in just a few days. The disaster also disrupted weather and caused food shortages worldwide, affecting millions. That eruption was the biggest in recorded history. It blasted a massive cloud of particles into the sky. Those particles blocked sunlight, cooled the planet, and caused worldwide chaos. The year after the eruption became known as the Year Without a Summer. Temperatures plummeted, crops failed, famine spread, and a cholera pandemic broke out, leading to tens of thousands of lost lives. A shocking fact, the eruption may have even inspired Mary Shelley to write Frankenstein while stuck indoors during the unusually cold summer of 1816 in Switzerland. Now since then, many volcanoes have erupted, but none have matched Tambora's scale. Now, over 200 years later, scientists warn that there's a new supervolcano threat. Another massive eruption could be on the way, and the world might not be ready for it. So, while scientists seriously discuss the likelihood of the next volcanic eruption, experts are calling for urgent action to prepare before it's too late. So, the thing is, a massive volcanic eruption today could be even more devastating than the Year Without a Summer. Unlike back then, we're already dealing with all kinds of weather changes and a more fragile global system, which could make the effects even worse. Dr. Michael Rampino, a geological scientist, warns that the world is more unstable now, and it means that a modern-day mega-eruption could have even more severe consequences. But this time, greenhouse gases from fossil fuels may make the aftermath of such an eruption even colder instead of warmer. So we're talking about volcanic activity endangering humanity. Dr. Thomas Aubrey, a volcanologist, found that in a hotter, more turbulent atmosphere, the sulfur dioxide gas released by a volcanic eruption would spread faster and farther than in the past. This gas forms sulfate aerosols, which reflect sunlight and cause global cooling. Because these tiny particles would be more evenly distributed, they'd have a stronger cooling effect than in 1815. Another atmospheric scientist at Cambridge explains that the size of these airborne particles matters. It affects how they absorb sunlight, and in a future warmer climate, an eruption could make the surface cooling stronger by 15%. At the same time, there are still many unknowns. Scientists from the University of Geneva say that we're only beginning to understand the full impacts of such an event. It's also difficult to precisely estimate future volcanic eruption risks, since we have very little data on older eruptions. So, to understand past volcanic activity, researchers analyze ice cores from Greenland and Antarctica, as well as ancient tree rings. Those act as historical records of weather changes. These measurements suggest that several eruptions in the past few thousand years temporarily cooled the planet by about 2 to 2.5 degrees Fahrenheit. One of the most catastrophic examples is the 1257 Somalus eruption in Indonesia, which was so powerful that it likely triggered the Little Ice Age. It was a period of global cooling that lasted for hundreds of years. More recently, the 1991 Mount Pinatubo eruption in the Philippines slightly cooled Earth for a few years. Because this eruption happened in the satellite era, scientists were able to measure exactly how much sulfur dioxide was released and how it affected the atmosphere. But even with modern tools like satellites and seismic instruments, scientists still have difficult times forecasting the next big volcanic eruption. Luckily, even though we can't predict the exact timing, we can study worst-case scenarios to help authorities prepare. This includes creating evacuation plans and stockpiling food in case of global crop failures caused by volcanic cooling. The changes in weather patterns might make volcanoes more active. Melting glaciers can reduce pressure on underground magma, which will increase the chances of an eruption. Plus, more extreme rainfall, which is becoming more and more common, can seep into volcanic cracks and cause powerful steam-driven explosions. It can affect both active and dormant volcanoes. Because of these risks, researchers are now mapping volcanoes that are the most vulnerable to climate change. Their studies show that the highest supervolcano threat comes from such areas as Iceland, Chile, and Indonesia. Those are places where glaciers are melting quickly or rainfall is increasing dramatically. A 2022 study found that 716 volcanoes worldwide, that's about 58% of all known active above-ground volcanoes, could be triggered by extreme rainfall, increasing the likelihood of another mini ice age. Now let's get back to that Hunga Tonga Hunga Ha'apai eruption that occurred on January 15, 2022. Scientists have confirmed that it created the highest plume ever recorded. The volcano, located underwater in the South Pacific, sent an ash cloud 187,000 feet high. That's higher than any previously recorded eruption. What makes this eruption even more remarkable is that it was the first to ever reach the mesosphere. It's the third layer of Earth's atmosphere. The mesosphere begins at about 160,000 feet above Earth, where meteors start burning up and creating shooting stars. To measure the plume's height, researchers from the University of Oxford and RAL Space used data from 3 geostationary weather satellites. Before this, the record for the highest volcanic plume was held by Mount Pinatubo's 1991 eruption in the Philippines, which reached 131,000 feet high. Interestingly, this kind of measurement was only possible thanks to modern satellite technology, and a decade ago, no one would have been able to do this. Another volcano we should mention in relation to a potential global volcanic disaster is located on Iceland's Reykjanes Peninsula. Its latest eruption happened in November of 2024, leading to evacuations in nearby areas. The eruption began just after 11 p.m. with little warning. The volcano released orange lava from a nearly 2-mile-long fissure. Authorities ordered evacuations for about 50 homes and guests staying at the Blue Lagoon Spa Resort, a popular tourist destination southwest of Reykjavik. While air travel was not affected, officials still warned of potentially dangerous gas emissions spreading across parts of the peninsula, including the nearby town of Grindavik. Grindavik, home to 3,800 residents, has repeatedly witnessed volcanic activity, and past eruptions even damaged its infrastructure and forced evacuations. For example, in August 2024, a 2.5-mile-long crack opened at the Sunthun Kangigar crater near Grindavik. It led authorities declaring a state of emergency as lava flowed in multiple directions. Fortunately, Iceland's meteorological office reported that the latest eruption was significantly smaller than the one in August. Geophysics experts conducted aerial surveys and figured out that the situation appeared less intense than the previous eruptions. These days, Grindavik is not at risk, but the possibility of further developments cannot be ruled out. Scientists predict more volcanic eruptions.
Living on our beautiful planet might seem safe, but only until you start thinking of all those dangers lurking just around the corner or in the vast darkness of the cosmos. Let's see what may eventually lead to the end of planet Earth. With each new potential threat, it gets more and more terrifying. Consider yourself warned. First of all, let's talk about hypercane. This natural disaster can get really extreme. A hypercane is a theoretical hurricane of unsurpassed power. It would occur if the ocean became overheated as a result of climate change, or a massive volcanic eruption could trigger it. In any case, these conditions would create a hurricane, which, unlike regular hurricanes, would stretch way beyond the lower stratosphere. The speed of such a storm would reach 500 miles per hour. The pressure inside the hypercane would be so low that it wouldn't let it wear out as quickly as other hurricanes. The hypercane could last for weeks on end. But the worst thing? It would likely damage or even destroy part of Earth's ozone layer, and the hole could be the size of the entire North American continent. Then we've got super destructive tornadoes. A tornado is a violently rotating column of air. It usually extends from a thunderstorm and is in contact with the ground. Inside a thundercloud, warm, humid air rises upward and cool air falls down along with rain or hail. Such conditions can lead to the appearance of spinning air currents inside the cloud. Interestingly, these air currents start out horizontal, but at one point they can become vertical and drop down from the cloud, becoming a tornado. Some tornadoes are narrow, rope-like swirls, but others turn into wild funnels. Tornadoes are ranked with the help of the enhanced Fujita scale. A weak tornado normally lasts for a few minutes and doesn't move faster than 100 miles per hour. The next level is a strong tornado. Such whirlwinds can last for 20 minutes or so and have winds of up to 200 miles per hour. And then we can also have violent tornadoes. Those can last for more than an hour and move at a speed of between 200 and 300 miles per hour. On average, around 1,000 tornadoes occur in the USA every year. There's even a region that got named Tornado Alley. It's a 10-state area in the Midwest, but tornadoes can happen in any state. One of the most destructive natural disasters was the tri-state tornado in the USA. It was the world's longest-lasting single tornado that traveled 220 miles through Missouri, Illinois, and Indiana. At the same time, the average tornado's path is usually no longer than 5 miles. But what if one day, a tornado much bigger and way more powerful than any we've experienced before swiped through countries and continents? It would leave behind total destruction and devastation. And how about a supercell thunderstorm? It's the least common type of thunderstorm, but it's the most dangerous. It's likely to cause severe weather, damaging winds, very large hail, and even violent tornadoes. What makes supercells unique is a deep and persistent rotating updraft called a mesocyclone. Supercells can potentially last for hours and cause great havoc. An asteroid impact could end all forms of life on Earth too. If a space wanderer was large enough, it could cause widespread devastation, like it happened with the 9-mile-wide asteroid from 66 million years ago. It's rumored to have destroyed 3/4 of the planet's plant and animal species, including dinosaurs. Depending on the asteroid's size and the speed of its approach, the impact could lead to massive fires, tsunamis, and the eternal winter effect. It happens when the debris ejected into the atmosphere blocks sunlight and disrupts the global climate. Luckily, we'd probably notice such a large asteroid coming close to our planet with the help of our equipment long before the collision and would have enough time to get rid of this threat. It would be our very own sun that would bring our world to an end. Our star is a gigantic, constantly changing ball of molten gases. Every once in a while, it spews out bursts of energy, solar flares. They often go hand in hand with something called coronal mass ejections. Those are giant bubbles of ionized gas that can accelerate to incredible speeds. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with the temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. Scientists classify solar flares depending on how brightly they shine in X-rays. You aren't likely to notice the tiniest flares if you don't have special equipment. Medium solar flares lead to fleeting radio blackouts at the poles, but nothing too serious. It's X-class flares people should worry about. They cause the strongest and longest-lasting solar storms. Now, if you had gamma-ray vision, you'd be able to see immensely bright flashes. They occur every day, outshine everything around you, and then disappear again. Those flashes are gamma-ray bursts. One of them could wipe out Earth's atmosphere. The flash that might ruin our planet would most probably be born in a faraway galaxy during a merge of two collapsing stars. It would be immensely powerful and super bright. Still, 1,000 light-years from Earth, it'd already shine as bright as the sun. Our planet's atmosphere would try to protect us, but its natural shield wouldn't last. The radiation would be so powerful that it would literally cook the atmosphere. It would create nitrogen oxides that would destroy the ozone layer. Without this layer, ultraviolet rays coming from the sun would be hitting Earth's surface at full force. They would wipe out tiny plankton in the ocean. But these plankton produce from 50 to 70% of all oxygen in the world. So, with their disappearance, there would be a severe lack of oxygen, which would lead to the disappearance of life on the planet. In the end, the heat and ultraviolet light coming from the sun would turn the planet into a huge chunk of rock. And what if we came across a wandering black hole? You might know that a black hole is a region in space where gravity is so powerful that not even light can escape its clutches. Luckily, the nearest to us black hole is 1,500 light-years away. It seems that we have nothing to worry about until we learn about wandering black holes. Now, things definitely get way creepier. If such a black hole entered the solar system, Earth would be doomed. We wouldn't stand a chance against this space monster. In 2020, 13 wandering black holes were spotted not so far away from our planet. But not far away in space terms means around 1 billion light-years away, so we've got some time left. Plus, the possibility of such a disaster is very, very low. One day, a rogue planet might push Earth out of the habitable zone and into an extreme orbit farther from the sun. Then, the climate all over the planet would start getting colder and colder. Don't forget that the farther our planet is from the sun, the weaker the star's gravitational pull on our planet is. In the end, our beautiful Earth would get too far away from its main source of light and heat. It would turn into a lifeless piece of rock covered with a thick layer of ice. Or the sun might expand and turn into a red giant. If it happened, it would change the entire habitable zone of our solar system. The disaster would start with our star running out of hydrogen in its core. This would trigger a chain of reactions, which would eventually lead to the core of the sun heating up and getting denser. As a result, the sun would get way larger than it is now. During this transformation, the sun would swallow Venus, Mercury, and Earth. Look at this comet! Recently, it's erupted 4 times in less than 48 hours and has become nearly 300 times brighter than normal. This is the most powerful set of eruptions the comet has had in over 3 years. Should we worry here on Earth? Well, I wouldn't say scientists are worried. They're super excited. First, let me give you a little background. 29P is what astronomers call a Centaur comet. Those are icy objects that orbit the Sun in the space between Jupiter and Neptune. What's interesting about centaurs is that they're kind of like cosmic hybrids because they're moving from one kind of space body to another. They start their life as far-out objects in a lifeless, freezing cold zone beyond Neptune. But then, over a few million years, they move inward toward the Sun because the planets of the solar system affect them with their gravity. Eventually, they turn into short-period comets. This term means they can pass close to the Sun and then slingshot back out into those icy regions. Centaurs, and their name indeed comes from a hybrid half-horse, half-human creature popular in Greek mythology, are especially interesting because they're basically leftovers from the formation of our solar system, kind of like cosmic fossils. Since they've been hanging out in the frigid outer solar system for so long, they've kept a lot of the volatile materials that were present when the solar system was first forming. This makes them a valuable clue in understanding how our solar system evolved. That's what makes scientists so enthusiastic. Now, about 29P itself. This thing is huge for a comet. It's about 37 miles across, which is almost 3 times the length of Manhattan. Now, worry not, it's too far away to cause us any harm. While it's one of up to 1,000 known centaurs, 29P is also in a rarer group of comets called cryovolcanic comets. Those are a fascinating class of space objects that have unique geological activity. The thing is, Cryovolcanic comets not only contain a unique mix of ice, dust, and rock, but also feature cryovolcanoes, aka cold volcanoes. They erupt with volatile materials like water, ammonia, or methane instead of molten rock. As for regular comets, when they approach the sun, the heat from the star evaporates their gases, leading to the emissions of dust and tiny particles, electrons, and ions. These materials create those magnificent trails. These eruptions are incredibly spectacular and make the comet appear a lot brighter since the cloud of cryomagma reflects the sun's light. The cloud that forms around the comet is called the coma, and it can grow so large and bright that it makes the comet look like a fuzzy ball of light. If you've ever observed a comet, the coma is the halo you see around it. Such eruptions are pretty unpredictable. While most cryovolcanic comets follow elliptical orbits that take them far out into the solar system, 29P is on a more circular orbit, staying around the same distance from the Sun as Jupiter. You'd think that this would mean its eruptions would be more regular, but that's not the case at all. In fact, 29P erupts in a completely random and unpredictable way, and scientists are still trying to figure out why. The latest outbursts started on November 2nd, 2024, when 29P erupted for the first time in almost 2 years. This was followed by 3 more large eruptions in less than 48 hours, which really got the attention of astronomers at the British Astronomical Association. They'd been tracking 29P for a while, and they reported that the eruptions sent out a cloud of debris reflecting about 289 times more light than the comet's nucleus, which is a huge increase in brightness. Astronomers are expecting that the coma, which is growing after each eruption, could take on an unusual shape. The multiple outbursts might cause the coma to expand in a weird, irregular way. This is especially interesting because 29P hasn't had a major eruption like this since November 2022. Then it threw out over 1 million tons of debris. The last time it had a massive outburst was in September 2021, when the comet had multiple eruptions in quick succession. In addition to the confusion about its eruptions, 29P is pretty different from most other comets. Most comets have elliptical orbits that take them far out into the solar system. They spend decades, centuries, or even thousands of years far from the sun, only to erupt when they get close. But 29P doesn't do that. No, it orbits the sun once every 15 years and stays at about the same distance as Jupiter. This strange behavior makes astronomers even more eager to figure out what's going on with it. Another cool thing about 29P is that it doesn't ever get close enough to the sun to grow a tail like other famous comets, such as the once-in-a-century comet, Tsuchinshan Atlas, which has recently made headlines. It passed the closest to Earth in 80,000 years. NASA's James Webb Space Telescope has been keeping an eye on 29P, helping solve some of the mysteries about the comet. And it has recently made another groundbreaking discovery. It has detected jets of CO2, good old carbon dioxide, coming from the comet. This was the first ever detection of CO2 jets on this particular comet. Webb has also discovered a jet of carbon monoxide coming from the comet. It can tell us a lot about the composition of the comet and its outbursts. What's especially interesting is that the jets seem to come from different parts of 29P's nucleus. Even though Webb can't actually figure out the nucleus itself because it's too small to see in detail, the jets coming from different locations on the comet's surface suggest that the nucleus may be made up of multiple objects. These objects might have different compositions, and it's possible that the nucleus is more of a composite body made up of smaller chunks that came together over time. Strangely, astronomers haven't detected any water vapor in the comet's atmosphere. That's unusual because the atmospheres of most comets often contain water. Our comet might lack water vapor due to the extremely cold temperatures on its surface. It could prevent water from evaporating or vaporizing. 29P isn't the only thing that Webb is studying. The telescope has also been making some big discoveries about galaxies far, far away. For example, Webb has recently spotted a galaxy with a pretty complicated name which appeared about 1 billion years after the Big Bang. What's super weird about this galaxy is that the gas in it is shining brighter than the stars, which is really rare. This could be a missing link phase in the evolution of galaxies, something that could help astronomers understand how galaxies transitioned from the very first stars, called population 3 stars, to the types of galaxies we see today. The stars in this galaxy are much hotter than we see in modern galaxies in local universe, around 144,000 degrees Fahrenheit, compared to the typical 72,000 to 90,000 degree Fahrenheit of stars today. This could mean that the galaxy is in the middle of a super brief but intense phase of star formation, where huge, hot stars are popping up in a dense gas cloud. And this gas cloud is glowing so brightly because it's being hit with tons of light from these stars. The research team behind this discovery says that although the galaxy doesn't have population 3 stars, because the data shows it has too much chemical complexity, it still could be a guide for understanding how galaxies evolved, from the first stars to the galaxies we're familiar with today. There are still so many questions about this galaxy. Is it a rare phase, or is it something that happens often in the early stages of galaxy formation? Astronomers are hoping to study more galaxies like this one to figure it out.
Breaking news! Turns out that potentially habitable planets aren't as rare as we thought. Scientists found out that they were wrong about how water appeared on Earth. So let's see what these new discoveries tell us about life in the universe. Water is essential for life, and scientists are always on the lookout for other habitable planets and stars with it. But did you know that Earth's water might have come from outer space? Recently, they took a sneak peek at a young star called V883 Orionis. This star is located about 1,300 light-years away from us, and they spotted something incredible: water vapor surrounding the star. Of course, they decided to study it, and that's when they realized that the composition of this water is remarkably similar to the one in our own solar system. This discovery, among many others, confirms that Earth's water was brought to us from space. But how exactly did it happen? And where did it originally come from? When a star is being born, it's surrounded by a big cloud made of gas and dust called a molecular cloud. It's like a cosmic fog. Inside this cloud, there are special things floating around, including water vapor. Now, where does this water vapor come from? Well, new water molecules could form in molecular clouds through some fancy chemical reactions. Most of the water vapor originates near the surface of the cloud, and that it doesn't extend into the cloud by more than about 1/100th of a light year, probably because it turns into ice. Now, in the really cold and crowded parts of these clouds, the water vapor can turn into ice and stick to tiny particles of dust. And together, these dust particles create something else: a special disk called a protoplanetary disk. This disk of gas and dust is like a cozy blanket surrounding the star, and it's made up of tons of little particles with ice on it. As the dust particles bump into each other and stick together, they come together and form bigger and bigger objects: comets, planets, and other celestial objects. And, of course, some of those pieces become comets and planets like the ones in our own solar system. V883 Orionis is like a fantastic laboratory for investigating this. Around this superstar, there's also a protoplanetary disk. Scientists had a feeling that when these young stars get really hot, they might release bursts of heat that can turn some of that frozen ice into water vapor. They wanted to investigate this exciting idea. To make sure they were right, they used a super powerful radio telescope called ALMA to look at V883 Orionis. And guess what they found? They detected water in the form of gas in that system. So the idea turned out to be correct. They also compared the amount of our regular water to the one found in that disk. The space water turned out to have a heavier form of hydrogen called deuterium. It was the first time we compared our water to an interstellar one. By doing this, the scientists were able to finally make connections between the water in that star, the comets in our solar system, and the one in the early stages of star formation. Okay, now we know where water comes from in the universe. It's formed when hydrogen and oxygen combine together in all sorts of cosmic clouds of dust and gas. And usually first it's ice. Although sometimes the hot breath of stars can melt it and turn into vapor. Anyway, these pieces of ice fall on particles of dust and rock. The little particles grow for a long time and form into comets, asteroids, and so on. And then these comets and asteroids spread water across the universe. But how did the water get to the Earth? Well, scientists used to think that it was brought to us by comets and asteroids. They crashed into our planet a lot and eventually brought a lot of water to it. But now that we learned more, they have a new theory. Now they believe that Earth, rather than relying on icy comets, greedily sucked up water from its surroundings. Around 4.5 billion years ago, when our sun was a young star, it was also surrounded by a protoplanetary disk. So, the process of forming water in our solar system worked just like we discussed before. In other words, we also had some icy particles within our solar system. And Earth, like a celestial sponge, absorbed these ice and vapor from its nearest surroundings. It quenched water from teeny tiny pebbles floating around. What a thirsty planet! And this entire process took just a few million years, not hundreds of millions of years like we previously thought. Why is it important? Because it changes our understanding of how life can form in the universe. We used to think that planets with water on them were super rare. We thought that they had water delivered on them through tons of collisions, that it should take hundreds of millions of years, that the planet should be super lucky, and so on. If that were the case, the chances of finding water on planets beyond our solar system would be very low. But we were wrong. To come up with this fascinating idea, the scientists looked at more than 60 space rocks and planets to understand their makeup. They focused on something called isotopes, which are different versions of elements. By studying the isotopes, they discovered how planets form and how long it takes. And that's how they found a close link between Earth and other rocky objects in our solar system. That's why they now believe that planets similar to our Earth, rocky ones, actually have a pretty big chance of having some water on them. Moreover, let's look at any star system with a star the size of our sun. If there's a planet orbiting this star and the distance isn't too far or too close, then this planet most likely contains some water. This groundbreaking theory has exciting implications for the search for life in space. Habitable planets around other stars could be more common than we ever imagined. But that's not all. There's another salty discovery about water. Scientists found itty-bitty grains of salt in an asteroid. These salt crystals are definitely from space and look just like the ones in your kitchen, only super tiny. The S-type asteroid called Itokawa came back to Earth on a spaceship called Hayabusa. It's shaped like a peanut and hangs out near Earth. It probably broke off from a bigger space object. This type of asteroid is usually thought to be dry, but little salt crystals could only have formed in the presence of liquid water. So this discovery is shaking things up and making us think that there might be more water in asteroids than we thought. Scientists think that frozen water and other substances gathered on the asteroid's surface, but then the heat from radioactive decay and many meteorites hitting the asteroid made it warm enough for the frozen water to turn into liquid. Imagine all that chemistry action happening on a space rock. Well, would you look at that? Another discovery that's challenging the idea that water could be brought to us only by something from beyond our solar system. Looks like even the ordinary asteroids closer to the sun could have water too. If you think about it, many of our recent discoveries have hinted at this. For example, we know that there must have been water on Mars at some time. We also know that there probably were entire oceans on Venus a long time ago. And of course, even now in our solar system, there are lots of objects full of ice. So if there is plenty of this life elixir in our own solar system alone, it would be strange if there was no water anywhere else, wouldn't it? So let's hope that we've just unraveled a new chapter in our understanding of Earth's origins and expanded our hopes of finding other habitable worlds out there. Stay tuned for more discoveries.
Deep under the Indian Ocean, there's a giant patch where gravity doesn't work like on the rest of the planet. I mean, the gravitational pull works constantly, but Earth is not a regular sphere. Its surface is not smooth. It's covered with lumps and bumps like a potato, because our planet is not the same everywhere inside. Some parts are denser than others. Let's say you could pour water across Earth's surface. The shape this water would make is called a geoid, and it's like that because of the differences in materials inside the planet. That's why gravity isn't the same everywhere. And down there in the dark depths of the Indian Ocean, it's weaker than usual. That spot is something we consider a giant gravity hole that stretches more than 1 million square miles in size. It's roughly where the ocean floor sinks down in a giant depression. Scientists used ships and satellites to figure out this mystery. They realized the water level near India was lower because of this weak gravity spot. They're still not sure what made gravity become so weak in that area. But 2 Indian researchers realized everyone was trying to understand this, considering what that area looked like in the present. So they decided to go to the past. They used computers to make models of a virtual Earth and figured out that the answer could lie over 620 miles under the surface. That's where a part of an old ocean sank 30 million years ago, causing a hot melted rock to move around. And this mixture might have made gravity weak in that area. It's a really interesting idea, but it's still not the final answer. In 2018, a team of scientists from India went to the Indian Ocean with special machines to listen to the ground rumbling, similar to when you hear thunder. They found out there were hot streams of melted rock coming up from deep inside Earth. Could they be part of the reason why the gravity is weak there? We'll need more information to understand the issue better, maybe even go back further into the past. For instance, about 140 million years back, the land was all connected as a big piece called Gondwana. But then, India started moving away from it. While India was moving, an old ocean floor called the Tethys Sea sank into Earth's insides. These 2 scientists from India kept trying to solve the case, using computers to pretend to be going back in time. They checked how the land moved, as well as the mantle, which is basically a thick layer of hot, solid rock. The duo found out that a long time ago, there were hot, light rocks rising from deep inside Earth. These rocks created a spot where gravity was weak. This spot was like a big dent in the ocean floor. The more these rocks rose, the deeper the dent became. The first of these rising rocks popped out around 20 million years ago to the south of the weird gravity dent. As these rocks moved and went under the land, the dent got bigger and stronger. The 2 scientists think these rocks were pushed up by the sinking old ocean floor, like bubbles. This process disturbed something called the African blob. You gotta see this. Deep inside our planet, there are 2 very big blobs, like giant pieces of rock, as large as continents. One is under Africa, and the other is under the Pacific Ocean. These blobs have roots that start almost halfway, 1,800 miles, toward the center of Earth. And they're probably the place where columns of hot rock rise up from way down below. When these hot rock columns reach the surface, big volcanic eruptions happen. And we're talking about some really massive ones that might have even played a role in erasing dinosaurs from the face of the Earth a long time ago. So, we don't want these giant blobs to be disturbed. Anyway, not all scientists agree with the theory about why gravity doesn't do its job in this particular spot in the Indian Ocean, saying they need more proof to be sure about these rising rocks. The real answer might come from listening to Earth's rumbling. Plus, who knows if this gravity hole will stay there forever or move away. It depends on how Earth's mass will shift around. To see some changes might take a very, very long time, maybe even hundreds of millions of years. That's not the only region where gravity works in mysterious ways. Or at least, That's what it feels like when you see certain things around the world. Like, what if you saw rocks that don't sink, but can float on water for a very long time? They can even travel around for thousands of miles until they finally find a spot where they sink. Scientists figured out how this worked by using special X-rays to check the insides of these rocks. And these unusual rocks turned out to be very light and full of tiny holes. Researchers used wax to cover pieces of these rocks and went with a special X-ray method to look inside the rocks to see how much water and gas was there. The reason these rocks can float is because of something called surface tension, which is like a very thin, the size of a human hair, layer of air on the water's surface. This helps some animals, like lizards and insects, to really walk on water. And these floating rocks are not just cool because they travel, but also because they can actually help scientists find underwater volcano eruptions. They can also carry living things across oceans since they tend to collect some plants and other things rich in nutrients. So it's basically like a free cruise, until you sink down at some random spot. No iceberg needed. Here you have floating rocks. And in Death Valley in California, there's a strange phenomenon where big rocks move across a dry lake bed and leave trails behind them. People wondered how this was possible for 60 years until the case was solved. Some thought there must be strong winds moving these rocks, or maybe even ice. But scientists found these winds aren't really strong enough to move such big boulders. They placed cameras on cliffs near the rocks, even though they were hard to reach. They did this for 3 winters in a row to study the temperature, rain, and wind in the area. Their idea was that ice might lift the rocks and let the wind push them. To test this properly, they put a rock in a container with water and sand and froze it. When they later pushed the container, the rock moved like it was on ice. This experiment helped prove their theory. And what's interesting is that the rocky area in Death Valley is similar to one of Saturn's moons, Titan. So these weird things on our planet may help us understand other phenomena, even in space. The reverse waterfall in England is an example of a spot with weird gravity too. You can find it not far from Hayfield. It has water that looks more like a fountain than a waterfall, considering it goes up toward the sky. But it turns out gravity doesn't have anything to do here. It's just the wind. It's so strong that when the water falls down, it catches it and pushes it back up. But where does this constantly strong wind come from? You can see a similar thing at Hoover Dam in Nevada, US. Try to climb up the dam, 726.4 feet, and pour some water out of a bottle. Not working? Yep, the water won't flow down as it normally would. It will fly up. You'll have the same result if you throw some light object from the same height. You will get it back. And this happens because of the strong airflow too. So these things seem like gravity is messing up with us, but there's always a logical answer behind that. Hopefully, we'll get one for the gravity hole in the Indian Ocean too.
Here's an idea for you. Can we move our entire planet? Our Earth is already moving by itself, and in 3 ways at once. It rotates around its axis, around the sun, and even rushes through space at an enormous speed, along with the entire solar system. But can we as humans do something to shift the movement of our planet? For example, what if we all run or jump at the same time? Well, let's see. Imagine if every person in the world, from every corner of the globe, decided to jump simultaneously. Sounds fun, right? You might think, wow, that's a lot of people. We could definitely make a difference. Maybe we could cause earthquakes, or even be able to make some impact on the entire planet. But unfortunately, that's not the case. In reality, with an incredible burst of energy, the Earth feels a gentle nudge, as if being tickled by the collective enthusiasm of humanity. Yep, that's right. Billions of people, and it's like the planet has been given just a playful pat on the back. Why is that? Here's where science kicks in. Let's do the math. The Earth's mass is around 1.3 times 10 to the 25th pounds. The average weight of a person is around 136 pounds. So if we consider that there are approximately 8 billion people on Earth, the total mass of all humans combined would be about 1 trillion pounds. This number has 12 zeros in it, so it's about half the Earth's mass. The impact must be massive, right? Nope. You see, while the mass of humanity may seem significant to us, it's actually quite small, even compared to natural phenomena like weather patterns and ocean currents. Ocean currents and tides, which are driven by the gravitational forces of the moon and the sun, have a much greater mass and gravitational pull than all humans on Earth. They can move vast amounts of water. The Gulf Stream alone is carrying about 30 to 150 million tons per second. And that's just one ocean current. Even the atmosphere of the Earth weighs much more than us. It's a number with 18 zeros. Don't forget that the atmosphere is also constantly in motion due to things like solar radiation, temperature differences, and the Earth's rotation. So, as you can see, even 8 billion of us is like a feather to the Earth. So, what happens when we all jump at the same time? According to physicists, the impact of our jumps, which seemed so powerful individually, actually cancel each other out on a grand scale. As we soar upwards, the Earth beneath us feels a push, but that push is counteracted by all the other jumps happening at the same time. So, in the end, the planet's solid and sturdy surface absorbs our jumps with ease and feels nothing. It's like giving a giant rubber ball a teeny tiny poke. Well, the planet may giggle a little, causing a tiny ripple or vibration, but it quickly settles back to its regular state, unperturbed. Alright, let's leave the fantasies about how we all jump at once. But there has to be a way for us to move an entire planet, right? For example, what if all humans suddenly started running? Let's imagine that we all decided to run in the same direction at the same time. Would we be able to make some impact on the planet's rotation or orbit? Yeah, unfortunately, no. We still don't have enough mass. Even if we were all sprinting at the same time, our collective force would be tiny compared to the Earth's gravitational pull. Although this isn't the only reason. The concept of angular momentum comes into play here as well. Imagine you're spinning around in a chair. Have you ever noticed that when you pull your arms in, you start spinning faster, and when you stretch them out, you slow down? That's because of the angular momentum. It's a way to describe how things rotate. It depends on two factors: how hard it is to start rotating and how fast it's spinning. When you multiply these two together, you get the object's angular momentum. Now, let's think about the Earth. It's a massive spinning ball, so it has a lot of angular momentum. This is because it's big, and it rotates pretty fast. But here's the cool part. Angular momentum wants to stay the same, unless something acts on it. It's like a cosmic rule. This is known as the conservation of angular momentum. So, the Earth's total angular momentum stays constant, unless there's an external force acting on it. And no, we're not that force. Our marathon, as enthusiastic as it may be, wouldn't have a significant impact on the Earth's overall rotation because we are part of the Earth itself. We're talking about something big and external here, like a huge asteroid or a dwarf planet crashing into us or something. But come on, there must be a way for us to move the planet. Well, in order to do that, we would need to apply a force that is greater than the gravitational force holding the Earth in place. And we definitely can't do that while standing on the planet. Even if every single person on Earth worked together to try and move the Earth, we would be hopelessly outmatched by its sheer size and mass. So this ambitious idea would require an enormous amount of resources and technology to accomplish. First and foremost, we would need to have access to a huge amount of energy. We would need a source of immense amount of force, and this force would need to be sustained over a very long period of time. Perhaps we could generate this energy through the use of advanced propulsion systems, like that sci-fi stuff that's typically used to propel spacecraft in books and movies. However, even with the most advanced propulsion systems, it would still be incredibly difficult. Or, for example, we might be able to construct enormous engines or thrusters that could be used to push or pull a planet in a certain direction. Making something like that is impossible for us now, but who knows what will happen in the future. So now, let's imagine for a moment that we somehow did have the strength to do that. We managed to move the planet, or even give it a mighty shake. Buckle up, because things are about to get crazy. The ground beneath your feet begins to tremble and jiggle like a plate of gelatin at a dessert buffet. As these powerful shakes reverberate through the earth, energy ripples out in all directions. Seismic waves travel through the layers of our planet, causing the ground to ripple and rumble like a roller coaster. These shakes would trigger a chain reaction of quakes and tremors, as if the Earth itself is doing a lively dance. Seismic waves would race across the globe, reaching faraway places and giving tectonic plates a jolt. The Earth's surface would crack and split, creating rifts and fissures in the land. Mountains would tremble and valleys widen as the Earth adjusts to the vibrations coursing through its core. The entire continents might change their positions. Buildings, bridges, and structures of all kinds would be put to the ultimate test. Their foundations would quiver, walls would sway, everything would collapse and be destroyed. Our little shakeup could also unleash the wrath of mighty tsunamis. Massive amounts of water would be displaced, forming colossal waves that would charge across the oceans with a thunderous roar. Volcanoes might awaken from their slumber. Their eruptions would paint the skies with ash and molten lava, adding a touch of drama to our already shaken world. They could release massive plumes of dust and ash, casting a shadow over the skies and affecting air quality. So, even a little shake, or a little extra movement of our planet, would disrupt the very fabric of ecosystems. Animal habitats would crumble, migration patterns would be thrown into disarray, and the intricate balance of nature would tremble, putting countless species at risk. The consequences would be catastrophic. So, all this effort was basically for nothing. Let's just leave our beautiful blue planet the way it is and appreciate its perfect movement.
So, astronomers have just announced that they might have found signs of possible life on a planet outside our solar system. Wow! This distant world is called K2-18b, and it sits about 124 light-years away in the Leo constellation. So, what life are we talking about? Little green men? Octopus-like tentacled creatures? Well, not exactly. First things first, let's define what life is. It's what distinguishes animals and plants from inorganic matter, like the ability to grow, reproduce, and change. Now, what do we need to support life? If what comes to your mind is water, bingo! Scientists have the feeling that K2-18b might be covered in oceans, and if it's so, it can support tiny forms of life like microbes. A team of researchers from the UK and the US used the James Webb Space Telescope to look at the planet's atmosphere. they found hints of two very special chemicals. On Earth, only living things can produce those, and the living things I'm talking about are mostly tiny ocean plants called phytoplankton. So, basically, this planet might indeed host life in the form of algae. Now, of course, scientists still need more proof before getting too excited. We should keep in mind that it's possible that those chemicals were made by something we don't understand yet, not necessarily by living things. But still. K2-18b is a big boy. It's more than 8 times heavier than Earth and about 2.5 times larger. So what makes it even more interesting is that it's located in the Goldilocks zone around its star. That means it's not too hot and not too cold there, just right for the existence of liquid water, which is highly important for life as we know it. Astronomers study faraway planets like this by watching how their light changes when they pass in front of their star. This allows us to figure out what kinds of gases are in the planet's atmosphere. Back in 2013, the James Webb Space Telescope found methane and carbon dioxide in the atmosphere of the planet. These are carbon-based molecules, and it was the first time they were found on a planet in the habitable zone. Scientists also saw a weak signal of a chemical called DMS, which is mostly made by tiny ocean life here on Earth. So, the researchers pointed the telescope at the planet again a year later using a different tool that could pick up more light details. This time, they found much stronger signs of DMS and some related chemicals. But the problem is the signals aren't strong enough yet. They haven't reached something called the 5 sigma level, a parameter scientists use to confirm discoveries. Plus, even if the DMS really is there, it doesn't automatically equal the existence of life. Scientists once found DMS on a comet, which means that it can be produced without some kind of life taking part in the process. And still, the amount of DMS on K2-18b looks way higher than anything seen on Earth. That's why some astronomers are sure it's coming from something living. K2-18b has been a top pick for what scientists call a Haitian planet. This term means a big, watery world with thick hydrogen atmosphere. It's not the kind of place where extraterrestrial civilizations like in movies would live. But it could be home to tiny life forms, like the microbes that once lived in Earth's oceans billions of years ago. Once again, not everyone agrees on how friendly K2-18b really is for life. Some scientists think planets like this might actually be too close to their stars to hold on to liquid water. K2-18b orbits its star every 33 days, which is pretty fast, and could mean it's too hot. That's why some experts claim that even if the planet has any water at all, it might be boiling. Or maybe it's not water, but oceans of lava. But most scientists agree on one thing: we should wait and see. With just 16 to 24 more hours of telescope time, astronomers could confirm what they've seen. This could happen in the next few years. And even if it turns out K2-18b isn't the world we're looking for, we're still getting close. With powerful telescopes like James Webb and more coming in the future, we might be able to answer whether we're alone in the universe or not. At the same time, some places in our own solar system, like Mars, Venus, or Saturn's moon Enceladus, might actually have a better shot at hosting life. Or we could keep exploring other promising worlds, like Proxima Centauri b, which is the closest exoplanet we know about. It's just 4.25 light-years away from us and orbits a small star called Proxima Centauri, right in the habitable zone. This planet is a bit bigger than Earth, which makes it a super-Earth. That's what we call exoplanets larger than ours, but much smaller than gas giants like Neptune or Jupiter. Proxima Centauri b is a fast-moving world. It needs a mere 11 days to go all the way around its star. Scientists think Proxima Centauri b might have a rocky surface, and that's a good sign for possible life. On the other hand, its star blasts it with a lot of ultraviolet radiation. It might have already destroyed the planet's atmosphere, if there was any to begin with. So there's a big question mark when it comes to this world's habitability. Then we've got TRAPPIST-1e, another promising Earth-like planet. It's one of 7 rocky planets orbiting a small, cool star called TRAPPIST-1, about 39 light-years away. Discovered in 2017, it might be one of the most promising places to look for life beyond Earth. This planet is actually a bit smaller than Earth, with a mass around 1/2 that of our planet. It completes an orbit around its star in just 6 days, which is super fast compared to Earth's 365 days. The planet's size and density suggests it has a rocky surface, and that's another key factor when we talk about habitability. Even though TRAPPIST-1e is very close to its star, the star is quite dim and cool, so the planet might still have a stable Earth-like climate. Some scientists even think it could have more water than Earth. Let's move on to Kepler 186f, located about 500 light-years away. It was the first Earth-sized planet found in a habitable zone of another star. It orbits a red dwarf, which burns cooler and lives much longer than our Sun. This means Kepler 186f could have stable conditions for billions of years, giving life plenty of time to possibly form and evolve. The planet gets only about 1/3 of the sunlight Earth receives, so it would likely be cooler but still warm enough to keep water from freezing. It also seems to be a rocky planet just like Earth, which boosts its chance of hosting life. Now, how about visiting LHS 1140b, about 40 light-years away? This planet has about 5.5 times the mass of Earth. Scientists think it's rocky and possibly has a thick atmosphere, which is a big deal. An atmosphere like that can trap heat, keep temperature stable, and protect water from escaping into space. This world orbits a quiet red dwarf star, so it's not constantly blasted by harmful flares like some other exoplanets are. Some studies even suggest LHS 1140b could be an ocean world with lots of water. So it's one of the more exciting planets we've found in our neighborhood. And finally, we have Gliese 12b. Astronomers call it exovenus. It sits 40 light-years away from Earth. This world is about the size of Venus and orbits a cool red dwarf star. It needs just under 13 days to complete one orbit. The temperature on the planet is around 107 degrees, which is quite warm but still okay for life. The thing that makes Gliese 12b so interesting is that it could help us understand how Earth-sized planets around cool stars hold on to their atmospheres. That's important because an atmosphere is crucial for things like liquid water and protecting life from harmful radiation. According to some researchers, Gliese 12b is one of the best chances we have to figure out whether planets like this can stay habitable. In February 2025, scientists discovered something shocking about our planet's insides. We've long thought that Earth's inner core is a solid and stable sphere, but the truth may be quite different and a bit alarming. The recent study suggests that the surface of the core might be undergoing structural transformations right at this moment. Researchers from the University of Southern California have analyzed decades of seismic data and discovered that the surface of the inner core appears to deform under the influence of the outer core. We've observed such changes for the first time, but they're likely to explain some peculiarities in the rotation of the inner core. They could even be influencing the length of days on Earth. Now, the inner core of our planet, located about 3,100 miles below the surface, is traditionally described as a solid ball of iron and nickel. However, new data shows that its outer layer may be more malleable than expected. This discovery is based on the analysis of seismic waves from repeated earthquakes near the South Sandwich Islands. The researchers used enhanced resolution techniques to study these seismic signals. They observed anomalies in the waves and made an unexpected conclusion. There must be deformations on the surface of the inner core, and they could be caused by turbulent interactions with the molten outer core. Now, this outer core, composed of liquid iron and nickel, has a highly important role. It helps generate Earth's magnetic field. Before, we really didn't understand its impact on the inner core. But now, the new study shows that the turbulent movements of the outer core could disrupt the surface of the inner core, and that could cause changes in its shape. These disturbances might also explain the gradual slowdown in the rotation of the inner core. Scientists have been observing it since 2010. On the surface, we really don't notice these changes, but they could influence Earth's overall rotation and length of days. The study can help us understand better what's happening deep inside our planet, how the inner and outer core interact, and how that affects Earth's magnetic field and movement. Obviously, direct observation of Earth's core is impossible. That's why scientists use indirect methods, like analysis of seismic waves. It also allows us to deduce the structure and composition of the core. As these waves pass through different layers, they get deflected or stopped, and this can provide us with clues about the nature of the materials they encounter. There are also laboratory experiments. Researchers reproduce the extreme pressures and temperatures of the core and study the behavior of iron-nickel alloys. They use sophisticated instruments, such as diamond anvil cells, and they allow exploration of these extreme conditions. Then there are studies of meteorites. The thing is, some of them come from asteroids with a metallic core like Earth's. Their chemical composition sometimes provides clues about the elements present in Earth's depths. Scientists can also create numerical models. By combining seismic, experimental, and geochemical data, they simulate the internal dynamics of our core. But what would happen if Earth's core suddenly stopped spinning altogether? Well, it's unclear, but we can make assumptions. If it was just the solid inner core that stopped, the answer would be, not much. Even if it didn't just slow down its movements, which is happening right now, but stopped altogether, the main impact would be on the speed of Earth's rotation. Our days would get longer. Over time, it could weaken the planet's magnetic field, which would be bad news, but not as catastrophic as what would happen if the outer core stopped spinning. That's when things would get seriously bad. Without the rotation of the outer core, Earth would lose its magnetic field, and the loss of this protective shield would set off a catastrophic chain reaction. First off, tectonic plates would start colliding in chaotic ways. Imagine being on a bus when the driver suddenly slams on the brakes and you go flying into other passengers or on the floor. The planet would experience something similar, but with tectonic plates. Ew. These violent collisions would cause massive earthquakes along plate boundaries worldwide, shaking buildings, bridges, and roads. Water systems, electricity, and phone lines would be destroyed in the chaos. But this would only be the start. Without the magnetic field, cosmic radiation would start hitting Earth's surface. These high-energy particles from the Sun would interact with the oxygen and nitrogen in our atmosphere, damaging the ozone layer. This would allow even more radiation to reach Earth's surface, causing even more damage. Electronics would fail, power grids would collapse, and communication systems would go dark. But the effects wouldn't be limited to just humans. All forms of life would be at risk. Many animals, like migratory birds and turtles, rely on Earth's magnetic field for navigation. With it gone, they would be completely lost. Birds would lose their sense of direction, and turtles wouldn't be able to find the beaches where they need to lay their eggs. Luckily, we don't need to worry about this apocalyptic scenario anytime soon. The outer core of Earth is very unlikely to stop spinning in our lifetime or ever. So for now, we're safe. But to truly understand Earth, you need to go 4,000 miles beneath our feet. Earth has four main layers, from the very center to the surface: the inner core, outer core, mantle, and crust. Now, except for the crust, no one has ever explored these deeper layers in person. The deepest humans have drilled is just over 7.5 miles, and that took 20 years to achieve. At the very center of Earth is the inner core, a solid metal ball about 758 miles in radius, which is about 3/4 the size of the Moon. It sits about 4,000 to 3,200 miles below the surface. Made mostly of iron and nickel, the inner core is incredibly dense. It spins a bit more slowly than the rest of Earth and is intensely hot, reaching temperatures of 9,800 degrees Fahrenheit. It's like the surface of the Sun. The pressure there is staggering, over 3 million times greater than the pressure we feel on the surface. Some research even suggests that there might be an even smaller, denser core inside the inner core, thought to be made mostly of iron. The outer core is also made of iron and nickel, but in liquid form. It sits about 3,200 to 1,800 miles beneath the surface. The heat here comes mostly from the radioactive decay of elements, like uranium and thorium, causing the liquid to churn in massive turbulent currents. This motion creates electrical currents, which generate Earth's magnetic field. Interestingly, Earth's magnetic field reverses about every 200 to 300,000 years, and scientists are still trying to figure out exactly why it happens. The mantle is Earth's thickest layer, stretching almost 1,800 miles deep. It starts just around 19 miles beneath the surface. Made of iron, magnesium, and silicon, it's dense, hot, and semi-solid. To imagine it better, think about caramel candy. Like the outer core, the mantle also circulates, but it moves much more slowly. Closer to the upper edge of the mantle, between 62 to 124 miles underground, the heat is so intense that it melts rock. This creates a partially melted layer of rock called the asthenosphere. Geologists think that this soft, hot, and slippery layer is what allows Earth's tectonic plates to move and slide. Some of the diamonds we find on Earth come from the mantle. Most of these diamonds form at depths above 124 miles. But rarer, super-deep diamonds may form as deep as 435 miles. These diamonds are brought to the surface by a certain kind of volcanic rock called kimberlite. The outermost part of the mantle is cooler and more rigid, behaving more like the crust above it. Together, this uppermost part of the mantle and the crust are called the lithosphere. As for the crust itself, it's the outermost layer of Earth. It's about 25 miles deep and makes up only 1% of the planet's mass. And yet, it holds all known life in the universe. So, in the end, will the sun be to blame for destroying our planet? Or how about a huge meteorite? Or some kind of disease? Probably not. It seems that life will disappear for a very unexpected reason. Humans, animals, insects, fish, and most microbes will be wiped off the face of the Earth because of oxygen, or more precisely, because of its absence. Recent research has shown that the number of freshwater reservoirs with very low or no oxygen levels in coastal areas is increasing worldwide. Over the past 65 years, 4 times more oxygen-deficient waters have appeared in the world's oceans. What does it all mean? It's likely that life on Earth will vanish much sooner than the sun's energies dries up all the oceans. The end is likely to come in a little more than 1 billion years. But this doesn't mean that the planet will disappear too. The period when Earth is filled with oxygen will make up just about 20 to 30% of the total lifespan of the planet. So we're just temporary guests here. Just think how long that is, 1 billion years. The first Homo sapiens appeared only about 300,000 years ago. That is, the entire history of humanity occupies less than 500,000 years. So relax. 1 billion years won't pass very fast. By that time, humans won't be on Earth anymore. We might master space travel and find a new planet in the vast depths of space. But why can we lose air? As the sun heats up, the planet gets warmer and warmer, and this heat breaks down carbon dioxide, the gas which is necessary for all plants to photosynthesize. Without carbon dioxide, they can't produce oxygen. With a drop in carbon dioxide levels, the methane content will increase, and this gas is quite harmful to us. Now, this all sounds logical, but this is a secondary reason for the lack of oxygen. The real problem is something else entirely. As the sun becomes brighter, it will begin to heat rocks on Earth, such as granite and basalt. These rocks will start to break down faster. When they collapse, they take carbon dioxide from the air, which warms our planet. If there's less carbon dioxide in the air, Earth should become colder. But there's a problem. The sun will shine more, and its heat will outweigh this cooling effect. So even if rocks take away carbon dioxide, the sun will blaze so much that Earth will still become extremely hot. Next, when the sun shines more intensely, it, along with other natural factors, contributes to the breakdown of granite and basalt. These rocks mix with carbon dioxide and water to make carbonates, which go deep into the Earth. This takes carbon dioxide out of the air, which means plants can't make as much oxygen because they need carbon dioxide to do that. Besides, volcanoes release gases, which also reduce the amount of oxygen in the air. So the sun, by destroying rocks, affects what happens inside Earth and controls how much oxygen there will be in the air. In about 1 billion years, the sun will become so bright that no rocks will be able to save Earth from its heat, and the escaping gases will halt photosynthesis and oxygen production. And then, our planet will return to the state it was in about 2.4 billion years ago, to the time when the Great Oxidation Event began. And this event was much more important than, say, the first Olympic Games or the appearance of humans on the planet. Billions of years ago, there was almost no oxygen on Earth. Instead, there was a soup of gases, such as nitrogen, ammonia, methane, carbon dioxide, and others. Yes, we have these gases in the atmosphere today, but there used to be a lot more of them in the past. It was difficult for any form of life to originate in such conditions. But after some struggle, it succeeded. At first, Earth was inhabited by the simplest bacteria, including cyanobacteria. They learned how to make oxygen using sunlight, water, and carbon dioxide. These bacteria worked for millions and billions of years and made so much oxygen that it began to accumulate in the air. This was what we now call the Great Oxidation Event. It was like a great celebration of life, because with oxygen, new living beings could appear. But by the way, cyanobacteria didn't learn photosynthesis because they were like, oh, let's make oxygen, it's so cool. No, oxygen was just a byproduct. Cyanobacteria wanted only one thing, to get as much energy as possible. And for this, they learned photosynthesis. It helped them store energy using sunlight. They used special pigments to absorb light, and the result of this process was the release of oxygen. This had been going on for hundreds of millions of years, and then, at some point, they made too much oxygen. This oxygen started to spoil other gases that had been there before. For example, it ate a lot of methane. Because of this, Earth cooled down a bit, and the Ice Age began. But that's another story. In short, in 1 billion years, we risk going back to that difficult time. But let's hope that we'll manage to move to another planet on our spaceships or come up with some other solution. And what'll happen to our home planet next? Will new life be able to originate there without so much oxygen? Well, it's possible, but it'll be much more difficult. This will require another source of energy besides the sun. It can be, for example, hydrothermal vents. And by the way, there are ecosystems on Earth that use this type of energy. You can find one of them in the Mobile Cave in Romania. Imagine a place where there's little oxygen. It's dark. The sun's rays don't reach there. Over millions of years of evolution, a unique and slightly creepy life has developed in this cave. It was first discovered in 1986, and scientists are still exploring this place. The entrance to the cave is just a small hole in the ground. A narrow tunnel goes deep underground. Inside the cave, the air is filled with hydrogen sulfide and carbon dioxide, and there's half as much oxygen there as on the surface. A human can't stay there without a special mask. But for local forms of life, this is home, and they feel great there. There are several dozen species living in the cave, and many of them aren't found anywhere else on Earth. Here you can see strange little monsters, white snails, white spiders, centipedes with long whiskers, transparent shrimp, and even unknown species of leeches. Since there's no light in the cave, all these creatures don't need eyes. They're blind, but they have long sensitive antennae and paws that allows them to navigate in the space. They also have no colored pigment, so all these bugs and spiders are either white or transparent. But if there's so little oxygen there, and nobody does photosynthesis, then how does all this life survive? It's all thanks to the unique bacteria autotrophs. They absorb carbon dioxide and produce nutrients. These bacteria are food for other organisms, and those, in turn, become food for larger creatures. So a whole food chain has been built in the cave, which provides all the inhabitants with food. Evolution has created a unique ecosystem that exists separately from the rest of the world. It's like a small universe that has developed according to its own rules. However, this universe is not expanding. because all living beings here can't live away from hydrothermal vents and autotrophs. Otherwise, where would they get their energy from? But let's imagine that the sun cools down, almost all the oxygen disappears, and the entire planet gets covered with hydrothermal vents. It's dark, and the air is filled with methane, CO2, and other substances, and somehow life begins. Even people appear at one point. What would they look like? Pale, thin, and blind creatures with very long arms that help them navigate in space. They have pets, large centipedes or cockroaches that move silently on the ground. People are also quiet because they don't have lungs filled with air to scream. There's silence in the world. People communicate through touch. No one travels. Everyone lives separately next to their hydrothermal source. The whole world has turned into a horror movie in 1 billion years. So hey, take a look. This is our planet's crust, its outermost and thinnest layer. And here's the mantle. It's way thicker. And this is the core. Wait, what's happening here? Uh-oh. The core is leaking right into the mantle. Quickly, we gotta stop the leak. What do you mean it's been going on for millennia? Earth's core is actually a very intriguing thing overall. Its unique properties, ranging from housing a mysterious metal orb to being nearly as hot as the sun's surface. Well, another one on this list of enigmas, apparently, our planet's core is leaking gas. I can relate. Is it dangerous for us? Is it going to boom if somebody lights a match? Well, not really, all because this gas is a rare isotope called helium-3. Helium-3 is a version of helium with one neutron instead of the usual two. Most of helium-3 in the universe was created around the time of the Big Bang, so it's some pretty ancient stuff. As the solar system formed, this gas became trapped deep within Earth's core. Shielded from space collisions and other cosmic hullabaloo, it remained hidden in the planet's depths for billions of years. Now, we've known for quite some time that occasionally, trace amounts of helium-3 escape to the surface, but no one has known the exact mechanism behind this leakage. Until recently, the breakthrough came with the discovery of exceptionally high ratios of helium-3 and its more common counterpart helium-4 in ancient lava flows on Baffin Island. This island is located in Canada's remote Arctic archipelago. The craziest thing is that these findings have the highest helium-3 ratios ever observed on dry land. The research revealed significant helium-3 levels. It might mean that the volatile elements from the solar nebula, that's the cloud of gas and dust that gave birth to our solar system, have remained in Earth's mantle since the earliest stages of the planet's formation. The discovery was made in lava flows that erupted around 60 million years ago, during the formation of a new seafloor when Greenland and North America split apart. But hey, it was amicable. The research team, led by Forrest Horton from the Woods Hole Oceanographic Institution, used advanced techniques to measure the helium trapped in olivine crystals within the rocks. These crystals formed before the magma erupted, which helped preserve the helium as it rose from deep inside the planet. The scientists found about 10 million helium-3 atoms per gram of olivine. That's a shockingly high concentration for Earth. You see, Earth's core acts as a reservoir for helium-3, storing it since the planet's formation. Over time, small amounts of this gas escape into the mantle through processes like mantle convection. That's when the planet's rocky interior stirs and moves like boiling water. Magma plumes, which appear in the mantle and rise to the surface, carry helium-3 with them. When the magma erupts, most of the helium escapes into the atmosphere. However, some of it gets trapped in crystals within the lava. That's how scientists can later study its origin and movement. Now let's follow the journey of helium-3 in the Baffin Island rocks. It began at least 100 million years ago. Mantle plumes carrying the helium likely took tens of millions of years to reach the surface. It means helium-3 has been leaking from Earth's core for millennia. It also means that our planet most likely formed in a solar nebula containing helium-3 and other noble gases. Baffin Island is an ideal location for studying Earth's deep interior. Its volcanic rocks are remnants of ancient lava flows that erupted when the North Atlantic began to open. The researchers traveled by helicopter to the remote island, which boasts towering cliffs, icebergs, and even polar bears. Local organizations helped the team access the area and ensured their safety during the expedition. The discovery of helium-3 leaking from the core raises new questions about what other elements might be stored deep within Earth. Could it be significant amounts of other light elements, such as carbon and hydrogen? These elements are critical for life and could provide further insights into the planet's habitability and evolution. For instance, the core's lighter-than-expected density might be explained by the presence of these elements. Plus, understanding the movement of helium-3 could also help track the behavior of other gases across the core mantle boundary. But this isn't the only unexpected discovery about Earth's insides. Let's go to Turkey's central Anatolian plateau. There, Earth's crust seems to be slowly dripping into the planet's interior. This process, known as lithospheric dripping, is still shaping the surface geology of the region. Lithospheric dripping occurs when the lower part of Earth's crust, heated to a certain temperature, becomes viscous and begins to flow downward. Imagine a thick liquid like honey or syrup flowing into a bowl. Now you get it. Now, speaking of Earth, it's been happening over a long period of time. And as this material moves downward, it pulls the crust with it, causing the surface to sink. As a result, we see new depressions or basins. Once this gooey material detaches from the crust and sinks further into the mantle, the surface rebounds, causing the ground to rise. This cycle of sinking and rising is what creates the shifting landscape in regions like the Konya Basin in the central Anatolian Plateau. It is the very site where geophysicists observe signs of lithospheric dripping. The research team, led by Julia Anderson from the University of Toronto, first noticed unusual patterns in satellite data, including a circular feature in the region where the ground was sinking. After examining geophysical data beneath the surface, the team identified a seismic anomaly in the upper mantle and discovered a thickened crust beneath the Konya Basin. All this points to the presence of dense material, like a result of lithospheric dripping. The team's model suggests that the Konya Basin is currently in the later stages of this process. While the surrounding central Anatolian Plateau has been uplifting over the past 10 million years, the Konya Basin is sinking at a rate of about an inch per year. While this number might seem small, it is quite significant in a region that is otherwise rising. Earlier studies have shown that the central Anatolian Plateau has risen for around a half-mile over the last 10 million years. It likely happened due to lithospheric dripping. However, the discovery of the Konya Basin reveals that this process is not one time, but can occur multiple times in different regions. The initial drip that formed the central Anatolian Plateau likely caused daughter events, which led to the formation of the Konya Basin. To validate their model, the researchers conducted a cool lab experiment. It simulated the lithospheric drip process. So, they took a tank filled with a highly viscous silicone polymer, which acted as a proxy for Earth's lower mantle. They also used a mixture of modeling clay for the upper mantle and ceramic spheres and silica sand to simulate the crust. A dense seed was inserted into the upper mantle layer to initiate the drip. Over the next few days, the researchers observed that the drip descended slowly. Within 10 hours, it began to fall. By 50 hours, a secondary drip had started. The results confirmed that, even without horizontal movement in the crust, the dripping process caused the surface to sink, forming a depression similar to the Konya Basin. This experiment has shown that lithospheric dripping can cause vertical deformations even without horizontal movements. Plus, it has proven that one event can trigger more drips that can change Earth's surface. This discovery helps scientists better understand how Earth's crust behaves over long periods of time and how tectonic processes can affect the landscape. Now, how about a bonus fact? In 1692, Edmund Halley, that guy famous for Halley's Comet, suggested that Earth might be hollow. He imagined layers beneath the crust with two concentric shells and a core about the size of Mercury, all floating in glowing gas. He even went further, speculating that these inner layers could be inhabited. This wild idea inspired Jules Verne's famous novel, Journey to the Center of the Earth. Wow!